Welcome to this episode, in which we will be discussing compound interest, using the compound interest formula, and using effective and nominal interest rates. We will discuss the difference between effective and nominal. Now, before we go into using the compound interest formula, I'm going to use an example where we calculate the future value of an amount at the end of a specific period. So in this example, if I deposit $500 into a bank account earning 1.5% per annum, how much will be in the account at the end of 3 years? To calculate this, I'm first going to work out the amount at the end of the first year, then at the end of the second year, and then at the end of the third year. So at the end of the first year, the future value is equal to the initial amount of the deposit, which is $500, plus 1.5% of that 500. Now you'll see $500 is common to both terms, so we can factorize that out. So we have 500 multiplied by 1 plus 1.5%, which is equal to $507.50. I now want to calculate the amount at the end of the second year. So in this case, I take the initial amount of $507.50 at the beginning of the second year, and I add 1.5% of $507.50 to that amount. Again, I can factorize out the $507.50, and so I have $507.50 multiplied by 1 plus 1.5%. If you recall from the calculation at the end of the first year, $507.50 was equal to 500 multiplied by 1 plus 1.5%. Now this is being multiplied by another 1 plus 1.5% to get us to the end of the second year. Because those two brackets are the same, we can write it as 500 multiplied by 1 plus 1.5% squared. And that is equal to $515.11. I now want to calculate the value at the end of the third year. So I take the $515.11 and I add 1.5% of $515.11. And just like in the previous steps, we take out the common amount, which is $515.11, through factorization, and we multiply that by 1 plus 1.5%. Now from the calculation at the end of the second year, we know that the $515.11 was actually equal to 500 times 1 plus 1.5% squared. We're multiplying that now by another 1 plus 1.5%. Because those two brackets are the same, we can write this as 500 multiplied by 1 plus 1.5% to the power 3, which is equal to $522.84. So from this we can see how the general formula is derived. Future value is equal to the present value multiplied by 1 plus the interest rate raised to the t, where t is equal to the number of years. We will next discuss the concept of nominal interest rates. Very often interest rates will be quoted as a percentage compounded a certain number of times per annum. So for example, interest rates might be quoted as 4% per annum compounded monthly. When a nominal interest rate is quoted, the symbol for the interest rate can be written with a subscript, which indicates the number of times per annum that the interest is compounded. So in this example, we have I subscript 12, because the interest is being compounded 12 times per annum. So we take 4% and we divide it by 12, and we have 0.33% per month. This is particularly useful when you are making regular monthly deposits into a bank account and you'd like to, for example, know how much you'll have at the end of the year when making monthly deposits. So the future value formula can now be written as future value equal to the present value multiplied by 1 plus the nominal interest rate divided by the number of times that interest is being compounded per annum, raised to the number of times, n, that the interest is being compounded per annum, multiplied by the number of years. This will become a little clearer when we go through an example. If I deposit $500 into a bank account earning 4% per annum compounded monthly, how much will be in the account at the end of 3 years? We're going to use the formula to calculate this. So at the end of 3 years, we know that our future value formula is equal to the present value multiplied by 1 plus I divided by n raised to n times t. So the present value is equal to $500 multiplied by 1 plus 4% nominal interest divided by 12 raised to the number of times that interest is compounding, which is 12 times per annum, multiplied by the number of years, which is 3. So now we have $500 multiplied by 1 plus 4% divided by 12, raised to 36 months in total. And that is equal to $563.64. We will next look at the calculation of present values from future values, and we'll do this both in the case of effective interest rates and nominal interest rates. So looking at the future value formula, we know that future value is equal to present value multiplied by 1 plus I to the t. In order to calculate present value, we can divide the other side of the equation by 1 plus I to the t, and if we want to bring the denominator up to the top, to the numerator, we can change the sign of the exponent and make it a minus t. Same thing with the present value formula with nominal interest. We know that future value is equal to the present value multiplied by 1 plus I divided by n raised to the exponent nt. So if we divide the other side of the equation by the bracket, we have present value equal to future value divided by 1 plus I over n raised to the nt. And if we want to put that denominator in the numerator, we simply change the sign of the exponent, and that becomes minus nt. So let's work out the present value using an example. Angela has $5,000 in her account at the end of 3 years. How much did she initially deposit if she was earning 2% per annum? So the present value formula we now know is equal to the future value divided by 1 plus I to the t. Substituting the values in, we have 5,000 divided by 1 plus 2% raised to the exponent 3 for 3 years, which can also be written as 5,000 multiplied by 1 plus 2% to the negative 3 if we bring it up into the numerator, which is equal to $4,711.61.